Welcome to Nerd Out at Spotify, where we bring you behind the curtain of the world's most popular audio streaming subscription service. Machine learning, open source, clouds, tabs versus spaces. We'll talk to Spotify engineers about interesting tech issues, big and small. A lot of Spotify's open source projects are tools meant to be used by developers, like frameworks for building data pipelines, software that helps you reduce the size of your mobile app, and of course, Backstage, our platform for building internal developer portals, like the one that we use at Spotify. But the open source project we're talking about today is different. Basic Pitch is a machine learning model, but it's not just for ML engineers and ML researchers. It's an open source tool that musicians can use, whereas other machine learning models used to identify faces in photographs or recognize your voice and turn your speech into text. Basic Pitch uses machine learning to recognize the music you play on an instrument. It listens to what you play on your guitar, or tuba, or xylophone, or just about any other instrument, including your voice, and then transcribes the notes into a digital score that you can edit on your computer. Musicians know this tool as an audio-to-MIDI converter. MIDI is the name of the file format for digitized music notation. And if you're a musician, this can make a real difference in your creative process. Instead of writing out notes by hand, you can just have Basic Pitch transcribe what you play. If you can play an instrument or even hum a tune, you can try it yourself right now at the demo site, basicpitch.io. Later on, we'll hear some music that was made with the help of Basic Pitch. But first, to find out what makes Basic Pitch so different from other ML models and why we open sourced it, I'm joined today by Rachel Bittner, one of the researchers from Spotify's Audio Intelligence Lab. She helped build the machine learning model behind Basic Pitch.
Yeah, I'm Rachel. I'm a research manager at Spotify. Most of when I did this work, I was a research scientist at Spotify. And I worked in a team that focuses on trying to understand things about audio signals using machine learning tools.
So first, tell me a little bit about the difference between a research manager and a research scientist.
The scientists are doing the work and the managers are like watching the work get done. No, it's a stupid joke. But yeah, as a manager, I'm more helping decide which research focuses we should take as a team, whereas before I was the one writing the algorithms and doing the actual research.
And then tell me a little bit more about the team and some of the things you do. Like you talked about research and ML things. You said a lot of very cool sounding things. What does that mean in practice? What are the actual things you do and things you produce?
You'll see one of the examples of one of the things we did in the team later on. But mainly, you can imagine there's a lot of cases where you have an audio recording and you want to know something about that audio recording, but it's hard with just a computer to look at the samples in the audio signal and know what's happening. So an obvious use case you could imagine is knowing what kind of audio this is. Is this a podcast? Is this a musical track? Is this meditation audio, etc.? So using machine learning techniques to understand what is happening in the audio one way or another. One classic example we like to give is in recommendations. So if there's a new track on Spotify, we don't have any information about what you might like based on what other people have said about this track or how other people have interacted with a certain track, which is called cold start recommendations. So one of the things that audio is really useful for is knowing how to recommend content that no one's interacted with yet. So the way we usually recommend music on Spotify is by looking at how people interact with the tracks. So if I listen to a song and I listen to a second song and you listen to one of those two songs, maybe you'll like the second song too. That's great and that works really well. But if you don't have that information, so if it's a brand new track that just got uploaded or if it's a track that not many people have discovered yet, we don't know what are the pairs of tracks that are going to go well together. So that's where audio can be really useful. So we can analyze the audio to know which things sound similar and recommend similar sounding content rather than content that other similar people listen to.
That sounds super cool, like fun, like researchy things. So yeah, you alluded to this earlier, but I want to talk to you about Basic Pitch and this kind of cool thing you've been working on. So can you tell us a little bit about it, what it does, why it exists?
If you were in music class back in the day, one of the problems you might have been asked to do is write down the notes of what someone is singing or what someone is playing. So writing that down in a musical notation. What notes did I sing? And that's a task that trained musicians can do, but it's not super easy for untrained musicians to do in the first place. And you can imagine that for really long recordings, that's a really tedious task to do. Like I know a lot of jazz musicians will sit and transcribe famous jazz solos, and they spend hours, and it's like part of their school training. But it turns out that we can do this with a computer and get machine transcriptions of these recordings in a computer readable format. And once we have these transcriptions in a computer readable format, we can create music with that.
Tell me a little bit more about why that's such an important thing to do. Like you talked about people doing this for hours manually and then needing machines to do it. Why do we care?
On the music creation side, a really common thing that people will do is they'll make a MIDI. The computer transcription format is called MIDI. So it's sort of like if you were to write down the words I'm speaking right now, we'd write it as like text, which the computer understands. And for music, the equivalent to that is called MIDI. It's a computer format for writing down like what are the musical notes in a recording. MIDI format is really useful, in particular for doubling. So if I have a recording of a saxophone, you can make a lot of really cool audio effects by doubling it with a MIDI track that does the same thing as that saxophone track, but augmenting it to give it a different sound quality. We'll show you some demos later of a bunch of different things you could do with MIDI, transcriptions of audio. Another side is just analysis. So knowing what's in a recording and being able to automatically analyze what's in there. And then I know some people also like to use it for like a training tool. So I'm going to sing into this system and see if I'm singing in tune or see how well I'm actually following a certain melody.
That sounds like a super flexible thing. And then at the same time, for each of those, I feel like there's something I've seen in the past that feels like it does something similar. I think you talked about effects and like changes you can make. Mm-hmm. That sounds a lot like the conversation I had with Peter earlier about pedal board.
Yes,
where it's like
absolutely.
You have some kind of audio and you can do an effect to it. Is that kind of using the same thing, or are these like completely different things?
They're not completely different, but most of the effects that Peter was talking about was like acting on the audio itself. So it doesn't need to know anything about what's going on in the audio necessarily. It can just act on generic audio. Whereas this, you'd actually be able to manipulate the sounding notes in the doubled effect. So for example, in a lot of singing recordings, you'll hear harmonies going on in the background. And imagine that you could first create a transcription of what the person's singing and then automatically create harmonies by doubling them and then moving the notes around to give you those harmonies right away. So that wouldn't happen with regular audio effects.
I gotcha. Yeah, this is well beyond my experience with playing with audio. So I'm having a hard time kind of understanding the difference between regular audio effects and effects that you need the transcription for, but it makes sense that there would be a lot more you can do if you have the transcription. Can you show us some of it? Like we can try playing with some of the effects, then you can tell us some of the things that you can only do with this.
Yeah, so maybe this is a good time for the demo in general.
Let's do it.
Demo.
All right, so Soundtrap is a digital audio workstation. So you might be familiar with Ableton or Pro Tools or Logic or GarageBand. Soundtrap is another one of those tools. They like to call it the Google Docs for music. And what's cool about Soundtrap in particular is it's built on the web. So you can use it online, you can share easily online instead of having to send huge files back and forth if you want to collaborate with someone else or bring someone physically into a studio to that computer. You can just collaboratively edit things remotely, which has been really cool during COVID. I used it myself a lot to make music with friends when we couldn't be together. Okay, so I have a Soundtrap session open, and I don't know what I'm going to play yet, but I think it's going to be Hot Cross Buns. Are you ready?
Oh, we're ready.
We're ready. I am singing cross. That's not the song. Okay, trying again. Hot cross buns, hot cross buns. Another great Hot Cross Buns recording. So I have a recording of this, so I'm going to go ahead and export it and then upload it into Basic Pitch. So it's processing. Okay, and I have a transcription now of Hot Cross Buns. I'm going to adjust the sliders a little bit, and it did a perfect job. Good job, us. And that gives us this nice little MIDI file. So that's just playing back the MIDI information with a particular synthesizer. So I can change that synthesizer to be something else. So you can imagine as a music creator, you could use this as a tool to change the sound around and play around with it. So now I'm going to download this MIDI file and upload it into Soundtrap. And we can listen to that together. Hot cross buns, hot cross buns. And you can see, you won't see this over audio, but we're also capturing the pitch bend. So I tried badly to do vibrato at some point, and you can see the wiggle of my notes as I'm trying to shake the pitch a little bit. So this is, played back as a clarinet. And then something I could do, make these like a third up or a fifth up. So I'm going to just boost them to be a third up, which would be what? B flat. So let's see how this sounds with my voice, trying to harmonize. Hot cross buns, hot cross buns. So that last one sounds bad. I'm going to bring that down let's hear that bounce. Hot cross buns, hot cross buns. Beautiful. So this is ukulele. I don't play ukulele. So disclaimer, I'm going to play like 2 chords. Okay, so then this is what it sounds like. A little bit distorted, but that's fine. And if I upload it into basic pitch, let's see how it does. So one of the things you might notice in this is it didn't get it completely right. It got a couple notes that are like lower that aren't actually part of the recording. So I can get rid of those by increasing the minimum pitch. So I don't know exactly which pitch those are at, but if I increase it up to here, then look, those notes go away. And it looks like probably the note segmentation can be increased a little bit because there's a little bit too many notes that get split up. So if I increase this up to like something a little higher. It's okay. Yeah. Then we can download it and put it in Soundtrap. Playing them together. And that's doubled with the Rhodes. And we can play with this and change it to a cool synth. Maybe not that one. Let's do a lead. Get this cool beautiful. The web browser version of Basic Pitch allows you to just download the MIDI that it transcribed on your web browser. And once I have that file, I can upload it to any DAW digital audio workstation, including Soundtrap, which is what I'm using right now. And there it is.
So I guess maybe the big difference that I was trying to figure out earlier between the type of effects you can do with pedal board and the type of effects you can do here is it sounds like pedal board doesn't change like the basic sound, but it can make it do different things like echoes and reverbs and things like that.
Yeah.
Whereas here you can really break it down and take like the basics of the sound and completely change what it is.
Exactly. Like you can delete the original sound and use the computer version as the new version of the sound, or you can layer them in different ways.
Yeah, that's really cool. During the demo, I think you said a few things. One thing I noticed is early on you said, I'll just quickly adjust the sliders over here. Can you explain what that even means and what some of the other things that you kind of had to do along the way?
Yeah, so like you can get a model working for like an academic paper or something, but then when you use it in the wild on all kinds of audio recordings, it's really hard to make a one-size-fits-all works perfectly system. What we did was expose some of the parameters of the model to the user in a sort of user understandable way, so that even on real recordings that might not exactly match what the machine learning model is used to seeing, we can still adjust it a little bit to get something that works for a user. So yeah, after I've recorded, put the recording into Basic Pitch, then there's this little menu that pops up that says Show MIDI Adjustments. So if I click on that, there's these 6 different parameters that I can adjust. One of them is called note segmentation. So one of the things that Basic Pitch is better or worse at, depending on the instrument and depending on the recording condition, is knowing when a new note is starting or when it's a single note that's just held out. So the basic number that we put as a default is 0.5, but maybe that creates too many notes. And actually in this case, my very first note, my hot in hot cross buns, was actually split into 2 notes initially. And so I adjusted that slider up a little bit to 0.75 so that those notes got merged together.
So then let's go back to basic pitch itself a little bit. Can you just talk about why this is a hard problem to solve? Why your team really even dug into it and there isn't like 100 tools that already do this?
Yeah, okay, I don't want to not give credit where credit's due. There are other tools that do many parts of what basic pitch does. What I think makes basic pitch special is it does a lot of things all in one tool rather than having to use different tools for different types of audio. So one of the things that has been researched a lot is, for example, transcribing piano recordings. So we have a lot of good data sets out there of piano recordings where we know what the notes are in particular, because there's this instrument called the disc clavier, which records MIDI while you play. So we have lots of audio recordings and paired MIDI files that we can use to create algorithms. So there's been a lot of research on transcribing piano for that reason. Similarly, we have some smaller data sets for guitar and some for voice, but they're smaller. So the majority of research has been focused on transcribing piano. On the other side, another line of research that's been focused on a lot is pitch tracking. So this is an old problem from, the 80s, the 70s. And that's focused on recordings where there's only one note or one pitch happening at a time. So you can use those constraints to get more accurate models and build around that.
Yeah, no, I was more trying to figure out a little bit more about what pitch tracking would be like in technical sense. Like, what is the computer trying to figure out?
So if I sang, you're going to hear me sing again. If I sang, my pitch was starting a little bit lower and then scooping up. And that pitch that we hear, you can map it to what's called the fundamental frequency. So the sound that my voice is making in terms of the audio signal that it is can be represented as a bunch of sine waves, where each sine wave has a particular frequency. And sounds that we hear as pitched often have harmonic content in them. So it won't just be the pitch I'm singing, but it'll also have content at the pitches above what I'm singing. And the hard thing about pitch tracking is knowing how to wrap all of those extra pitches down into the one that we actually hear as the main one. So that's more or less what pitch tracking is trying to do.
I'm trying to kind of wrap my head around this, like, there's multiple pitches and there's a main pitch, and like the thing that the software is trying to get out of that is really just like the main piece, or the rest of it is still important for like some part of creating, whether it's the MIDI or something else in it? It's
a great question. So if I just played back a recording that only had the main pitch in it, it would sound like a really boring pure tone, like doo, but less even interesting than that. Like you've probably heard like test tones before, like at the audiologist or something, where they just play little beeps into your ear. So that's like a pure tone. But then what makes two recordings of the same pitch sound different is all of those extra tones above it that we don't necessarily hear alone, that kind of get fused into like what makes my voice sound different from your voice if we were singing the same note.
I gotcha.
What we're trying to do in MIDI is just distill like what are those pure tones so that we can change the structure of the sound above it to sound like different things.
So like when you do things like change the instrument, is that pure tone the same, like regardless of the instrument, and it's the rest of it that makes it sound like a different instrument?
Yeah, so there's this concept of fundamental frequency, which is a tricky one because fundamental frequency is like a physical thing you can measure in a signal. Sometimes it's noisy and it's hard to know what it is, but it's measurable. And then the pitch that we hear is like a process in our brain. So there's a whole can of worms if we talk about what is the thing we hear versus the thing we measure. But the thing we hear, if we change the instrument in a MIDI file, is the same pitch. It's trying to have both the same fundamental frequency and the same pitch. I got into a can of worms very quickly.
And then you talked a little bit about there being ML models here and some of the parameters you're tuning. So why do we need ML to do this thing? It sounds like you're just trying to track down effectively a number. Like you have some sound, you're trying to figure out what the frequency is. Why is that an ML problem?
It's because sounds are different. Every sound is a little bit different. So if we were trying to track the pitch of my ukulele in the same room with the same microphone every time, I could build a system that didn't need ML necessarily. I could just build a really accurate model of when this sound happens, I'm going to measure it in this way, and I'm going to know that the pitch is this particular pitch. But then if we want something that's going to work with different microphones, with different instruments in different rooms, basically any kind of different sound color, we need some kind of machine learning to know what is important and what isn't in all of these different examples.
And so then what sort of model did you settle on? Tell me a little bit about the details of the ML that does that kind of... I'll stop.
Yeah, something I'm pretty proud of in this model is it's actually really simple. It's like kind of the opposite of what we've been seeing recently, which is like we're just going to make our models as big as possible. We're going to, throw a bunch of computational power. We're going to do a bunch of really clever machine learning tricks and make these really complex architectures to make everything work perfectly. And something that actually just came out of a practical product constraint is we wanted something that was going to be able to run on a web browser quickly. And to do that, you can't use, for example, what's popular right now is like transformer models, which wouldn't be fast enough to run in a browser efficiently. So this is actually just an old school convolutional neural network, which is a flavor of machine learning model that was one of the first types of models to start being good at modeling images, like knowing what objects are in images.
It's funny because when you started talking about it being small, my immediate thought was like, well, then it can't be some crazy, giant, deep neural network. And then you said use a convolutional neural network. And then I was like, I should go figure out more about neural networks then.
There's many flavors of neural network, big and small.
So tell me a little bit more about that. Why does it need to run on a web browser?
So we initially developed this with Soundtrap with the idea that if it's on the web, then more people can use it because not everyone has access to a DAW. Not everyone has access to a big GPU compute machine. And so basically by making it on a web browser in real time, we thought that would make it a better tool for users.
The idea was to build it into Soundtrap. I guess, is it built into Soundtrap somewhere now?
It may be in the future, but we don't want to make promises.
So you said it runs on a web browser.
Yeah.
I guess, does it require like anything crazy from your machine? Like, I don't know, it runs on a web browser, but you need to be on like a brand new $4,000 MacBook, or is it really like relatively generic computer, like a reasonable one that people would just own, it'll work?
It should even run on like a Chromebook. It shouldn't need any fancy machine at all. Yeah, that's the cool thing. It like right now, I would say like a common model size is something around like in the millions of parameters average. And then the really big crazy models that we're seeing today are like in the billions. And this is, I think, 15,000. So it's really like orders of magnitude smaller than most models out there. So it really doesn't feel like it's running machine learning. It feels like it's running a really simple process.
How did you get to this? Did you like start with this and it was immediately like a thing that ran on a web browser? Or did you have this path where it was like initially you were running in the cloud on like 100 GPUs and had to slowly figure out how to optimize it?
Well, what was funny about this is I started with, like when I build models, usually I'll start with a really simple baseline model. What is the smallest thing I can build that I think will work? And I started with that. And it kind of just worked. And then I was like, well, can I make it smaller? So I just kept making it smaller and it still worked. And so then I was like, oh, this is perfect. I ship it. It's done. So the initial goal was to make it fast enough and small enough, but I didn't initially come out with the goal to make it particularly this small. I just kept turning down the volume until it stopped working.
So tell me a little bit more about that. What does making it smaller and turn down the volume mean? Is this just like you gave it far less data or something else?
Yeah, I think the data is the thing that stayed consistent. So the model size doesn't depend on how much data there is. Like it will not work as well if there's less data for a really big model, but you could take a huge model with no data and it will still run. It'll just be bad. So in this case, the same data was used for all of the different iterations of this. But what it means is like the model itself has some number of free parameters, like knobs that it's turning to try to solve the problem. And if you just keep removing knobs, then it has less freedom to do it. But it turns out that this problem doesn't need that many knobs to get something working decently well in general.
So aside from just being able to run on a web browser on such a small footprint, were there other advantages to having this model be so small and different?
Yeah, the one thing that can be really beneficial to having smaller models is they don't take that much time to train. So you don't need tons of huge machines that train for weeks. I think this model trains in 4 hours on a single GPU. I could train it even on my laptop, which is huge because we're not using a ton of compute power and burning the forest for these models.
So it's not just that it can run on something simple, on simple hardware for the creators. It's also that on our end, we can rebuild it or retrain it and all that without taking a ton of cloud capacity and GPUs and stuff, even though you have a ton of data.
Exactly. You can run as much data as you want through a small model.
I see. So tell me about some of those knobs. Like what were the things that you either initially had and then got rid of and it still worked, or the things that were kind of had the most interesting effects?
Okay, this is going to require a little bit of background knowledge. So in a convolutional neural network, a common sort of stack is you'll have things called convolutions, which is essentially sliding filters that if you think about image processing, imagine you have an image and you want to blur it. You could run like a little blurring filter over that image. So imagine instead of a blurring filter, you're trying to learn what are those filters. And the number of those filters that you use determines how many of those knobs you have. So one of the simple things I did is just turning down how many filters that you use in each layer of the model. And the other simple thing is what you'll often do in convolutional neural networks is just stack these layers of filters. And if you just use less layers, then it's also smaller. So nothing too profound or deep, I should say.
The other thing on this optimization with a model topic, I think in the blog post where Spotify announced this thing, it talked, of course, about this using fewer layers and fewer parameters. But I think there were 2 bullets before that I just completely didn't understand at all. And it looked like they were research papers that also had your name on them somewhere.
Yeah.
And I'm going to butcher these, but there was one about like harmonic constant Q transforms.
Mm-hmm.
And the second one is something about jointly modeling onsets and frames and multi-pitch information.
Yeah.
What do any of those things mean?
So yeah, these are like my research babies, pet projects. So I actually did my PhD on a very similar topic. So that's like where my interest in this particular problem came from. So starting with this harmonic constant Q transform. First, I want to say that this was the idea of my collaborator, Brian McPhee, who I get too much credit for the harmonic constant Q transform. It was actually his idea. I just was the one leading that particular paper. But yeah, the idea is that there's a transform for audio called the constant Q transform, which takes audio and it maps it into a matrix. So you can think of it as an image where each pixel is telling you how much of one pitch is there at that point in time, sort of. And those images, constant Q transforms, could be used as input to a neural network. Now, before when I mentioned about pitch, how there's the tone, the fundamental frequency that's in a tone, and then there's all these other frequencies above it. It turns out that in physics, most sounds that we hear as pitched have harmonically spaced other tones above it. If I sing do, then there's actually a little bit of do and a little bit of da, and then da, da, da. I can't do it, but basically it's called the harmonic series. And it's like splitting the string in half every time. And what pitch would you get by plucking that string as you cut it in half? And basically, the harmonic constant Q transform is trying to more easily model the fact that structure is in pitched sound. Because in this matrix that we're creating, the distance in pixels between the pitches that are related is really far away. So between the first one and the second one, it's something like, 36 bins, depending on your resolution. The next one is 40 bins away from that. The next one is 60 bins away from that. And so for a neural network to model that structure, it needs to really see a lot of the content all at once. And that requires bigger models. So what we did with the harmonic constant Q transform is we create a third dimension. So instead of just having time by frequency in this one matrix, we create essentially a stack of matrices where now that third dimension of these spaced harmonics is aligned in the third dimension.
It sounds like what you're saying is you get this like super sparse matrix basically of like time and pitch. And then you try to, I'll use the word flatten, even though this completely isn't what you're doing.
Yeah.
Turning it into a much less sparse matrix by adding a third dimension that lets you say like, this pitch is way over there, if there's a value in this other dimension.
Exactly. And this way that the neural network can actually look along the third dimension instead of having to look up and down in frequency to get that information. So it allows you to use much smaller filters to see the same information. I have an analogy. It's like a staircase.
Perfect.
So if you wanted to be able to connect in an apartment building with many apartments on every floor, let's say you wanted to go from the first floor apartment A to the 12th floor apartment A. If you take the stairs, you have to go all the way up and around. You have to like go all the way through. But if you had like a fire pole that lets you go straight up and down, it's like much more efficient. You get to go straight there without having to pass through all the other apartments.
That totally makes sense for the third dimension thing, for like you're connected in the apartment. It's the crazy depth that exists in any effectively piece of audio, like you were saying, whether it's voice or music or whatever, the fact that it's dozens of pitches, or maybe not even dozens, I don't know, but like some crazy collection. That's the part that I really have a hard time wrapping my head around because I don't hear any of that. But once you break it down to the math and the matrices, that part makes sense to me.
A sidebar, there was like a whole type of art music that was called like drone music, where basically you listen to the same sound for hours. And your brain does a really cool thing when you do that, which is like, if I just listen to the sound of a trumpet playing a note over and over, your brain starts to pick apart and actually hear the different pitches in that sound that you don't hear when you just hear it quickly. One of the famous artists that used to do it is called Lamont Young. So if you want to blow your mind a little bit, go listen to some drone music, and I think you'll start to hear the structure.
How long does this sort of thing have to happen for before your brain starts to do that?
It's not that long. Like basically the longer you listen, the more your brain picks it apart. But it's like after a minute or two, you start to hear things that are different than what you heard at the beginning, even though the audio is exactly the same.
That's cool. I will have to try that. All right. Before we get too far away from what was the other paper, this jointly modeling onsets, frames, and multi-pitch information?
Yeah. So that's actually the paper that Basic Pitch is based on. So that kind of describes all of the different aspects of how Basic Pitch works. So the joint modeling thing is the idea that you can capture pitch at different layers of abstraction. So if I sing a melody, I sing hot cross buns, the pitch that my voice is doing is not completely flat in terms of the evolution of the pitch over time. Whereas if I played it on the piano, it'd be like, while that key is pressed, the pitch isn't changing. Whereas while I'm singing it, I'm not in tune. So I'm going like, cross buns. Probably I'm exaggerating, but you can model pitch to capture all of that deviation that might be in my voice, or you can try to capture sort of the little bit more structural level of what note am I trying to sing, which would be the flat notes. So a lot of transcription work in the past does one or the other. So it's trying to either model the wiggly stuff or it's trying to model the events. And what I tried to do in this work was model both at the same time. So trying to capture the notes and their deviation, which they're related. So there's some benefit to jointly modeling them too from the machine's perspective.
And then it just continues to blow my mind that you do this in a web browser on like commodity hardware like a Chromebook.
It blows my mind too. I didn't think it would be able to be this small of a model and still work.
That's super cool, I guess. Good work.
Good work, world.
So on that note, speaking of world, I guess Basic Pitch is open source, right?
Yes.
So tell me a little bit about that. Was that the plan from the start?
Yes, actually it was. Well, we wanted it to be open to the world in one way or another. And as we were developing it, it became clear that the best way to do that was just to put it on a web browser for the world without any constraints, not behind any paywall or any software. So what we decided to do is just put it no strings attached, both on GitHub, like the raw code itself, and a website that demos how it works in a sort of interactive way.
That's really cool, and seems like a thing that kind of very rarely happens. So then let's say, now that that's happened, what are people doing with it, both with the website and with the code?
I don't know yet. It's kind of new still. So I know people are using the website, and I've seen some cool threads on Twitter where people are transcribing solos or just seeing like what comes out of it when you try to stretch it to the limits, put something really complicated in there. Or I'd also mentioned before, like people seeing how in tune they're singing. So seeing if you sing Twinkle, Twinkle, Little Star, if it actually captures that you're singing a fifth or if it thinks it's like a tritone. And then on the creation side, we recently had Bad Snacks work with us to do a demo of what you could do with Basic Pitch. She's really great and interesting YouTuber as well as musician. She does a lot of like lo-fi music, and she also works a lot with music tech in general. She was honestly like the perfect person to partner with to showcase what Basic Pitch could do. And like really see her video. She did a really fantastic job of just showing what you could do with this kind of tool. And she made a really cool track, which I love.
That's cool. Yeah, we will definitely link to that in the show notes. What were some of the really cool things from that video that you really love?
So I mentioned at the beginning how like you could use this kind of tool to layer. So she did a lot of that. So she recorded herself playing a bunch of different instruments. So she had her harp, she she plays violin, and she took recordings of all three of those things. And then she converted them to MIDI with Basic Pitch, and then used those MIDI files to sort of layer the sound and make a much fuller, more electronic lo-fi feel to it. And my favorite part of that is in her violin solo, where she basically like the violin solo is just great by itself. And then she just beefs it up with all of these extra layers.
So we have the old timer blues lead. And I particularly loved this patch because I feel like it had the most similar expression to what I was looking for, while still maintaining an organic element. And just a lot of dirt, so much dirt. So here's what the outro sounds like.
And you said something about people pushing it to its limits. What sort of things are the limits?
So in the team, we actually built some demos ourselves too, which are on the About page of the demo website. And one of those demos is one of our research scientists pushing it to the limit. So he took a recording, I think, of a Beethoven symphony. Those sliders that we talked about before, he pushed them to kind of unreasonable points. So instead of trying to make something that's matching the audio, trying to like get as many notes as possible out of the system, even if they're not really there. And so then what happens is exactly all of these extra pitches that we don't hear. Basic pitch is not super confident that they're there, but it knows that there's something there. And so if you turn down the confidence value of one of those sliders to the very bottom, you get all the pitches almost, or all the pitches that are like there. And he made like a really cool, sparkly, jingly track out of all of these extra notes that emerged.
That's cool. This is this maximum shimmer one?
Maximum shimmer, exactly.
And I guess so that from the open source side, have you seen people doing anything interesting with the code?
So I know people have been asking how to turn it into a VST, a plugin format for digital audio workstations, so that you could directly use it inside the tool instead of having to go through the website, which is something we've wanted to do. We just haven't had the resources to do it just yet. But yeah, so if the community comes up with something, that would be awesome. And I know Bad Snacks also was asking for a way to use basic pitch in real time. So right now it runs faster than real time. It's just not written in a way that it creates notes in real time. It takes the whole recording and it does it in a batch, but it could be rewritten to be done in real time. And she wants to put it in the live workflow so she could play along with the MIDI that it's creating.
So tell me a little bit more about that. Like, what does it mean to play along with the MIDI that it's creating? Like, what does that change in the audio output that she is then creating?
There's a lot of artists that play with like live effects and live looping. Andrew Bird's a good example. Like he'll just be on stage and be making layers and layers and layers by himself and like playing them back and choosing what to play when and modifying the sound. And one of the components to that could be using a MIDI transcription of what you're playing to change the sound in a way that's unique.
I got you.
So maybe she plays something with her violin and then it gets played back as an electric guitar for the loops after that.
That sounds like, basic pitch would just get you the transcription in real time.
Exactly.
But then there's a bunch of other stuff that also has to happen effectively in real time, like the generation of the audio in that instrument and all of that. And like all of that technology already exists elsewhere.
Yeah, there's really great plugins for live playback and live effects.
Maybe it's the same answer for this, but what's next for basic pitch? What sorts of things are you guys thinking of doing next?
Well, in the very practical next step for us is we'd like to just get the training code out there, because right now we have the code out there for running the model. So you can see how it runs, but we don't have it easily retrainable. So I'd love to see how people could extend the research and push the boundaries of what it's doing. Because right now it's not perfect, and we could get something that works much better, I think, with some more research.
And so I guess all of this is still within your team, within Spotify, and what your plans are. So why is Spotify even investing in all of this stuff? Like, why does this help Spotify?
This could be a really useful tool for understanding better what the audio files in Spotify have in them for analysis or recommendation. Something I want to make clear also is we don't have any like ulterior motives for open sourcing this. We're not using this as like a Trojan horse to capture the information in people's compositions or to use the audio for something. Like, we're not storing anything. We just wanted to release it and see what people would do with it and see how it could get extended into other creative applications.
So it's less like a core part of any of our products and more just like we're doing interesting things in this space. We work with a lot of musicians and various types of audio creators. So if we have this tool and we're doing this research, we should give it to them and they will do great things. And then that will inevitably help us because we all work in this industry.
Exactly. They have better ideas than we do on what to do with tools, right? We might have one very narrow application and they'll come up with like much better, cooler things to do with it.
So I don't know if you can speak about any of it, but what other awesome things is your team working on that we should be getting excited about?
Very soon, we'll be releasing a feature in the tool called Anchor, which is a tool for creating podcasts. And the feature that we're adding to that is a button to enhance your audio. So to automatically remove background noise and make your voice sound better. So you could still like record in your car, or you could record while you're walking around and clean that up on the fly and post it without having to worry about your audio environment.
Cool. No, that sounds really interesting. It sounds like you guys are building a lot of really interesting things.
I'm lucky. I have a really cool team to work with.
Thank you so much for spending all this time with us and showing us all of this cool stuff.
No problem.
And I will do my best to try to understand at least half of it and like remember some of it.
Thank you for inviting me.
And now, here's the track that artist-producer Bad Snacks created using Basic Pitch. You can find a link to her channel in the show notes, and you can stream the entire track on Spotify. Try Basic Pitch yourself at basicpitch.io or contribute to it on GitHub. This is Virgo by Bad Snacks. So outside of your really cool team, what other things do you nerd out about?
Oh man, a lot. I'm an orchestra nerd. I play the flute and I play the bass. And in my orchestra, we're going to be playing Scheherazade by Rimsky-Korsakov soon. And I'm so excited. It's one of my favorite orchestra pieces.
Thanks for listening to Nerd Out at Spotify. Next episode, we'll talk about why Spotify's OSPO says open source work is work. What is an OSPO? Follow and subscribe, find out, and hear why Spotify is changing how we treat open source projects like Basic Pitch. Nerd Out at Spotify is produced by Spotify's Ted Vergakis and by Seaplane Armada, who also wrote our excellent theme song. I'm Dave Zolotusky. Thanks for nerding out with us.